All right, so we're going to move into Chapter 5 now. Chapter 5 is about conic sections and polar equations. It may seem a little bit strange why we're talking about conic sections in this class at all, but there are a couple of reasons that I can think of for why we would talk about conic sections. For one thing, all we've seen in this class so far, all we have reviewed so far, have been functions. But not all relations are functions, okay? And the conic sections are an important example of relations that are not functions. Some conic sections are functions, but most of them are not. So conic sections are examples of relations that are not functions. So it helps to sort of round out our understanding of relations in general. So that's one reason to look at conic sections now. Another reason to look at conic sections right now is that we've been looking a lot at polynomials. We just finished looking at polynomials and rational expressions. We talked about the fact that even transcendental functions can be rewritten as infinite polynomials. However, the polynomials that we've been looking at have been polynomials in just a single variable. If we wanted to look at polynomials in multiple variables, well, that's where conic sections come into play. Okay, so algebraically speaking, conic sections are all of the possible polynomials in x and y whose terms are degree 2 or less. So they're basically quadratic polynomials in two variables instead of just one. So in other words, a conic section is an equation of the form ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. That's sort of like the general form of a conic section. So we're going to go up to two variables, and we're just going to look at the simplest case of polynomials in two variables, and that's quadratic polynomials in two variables. And that's what conic sections are. They're quadratic polynomials in two variables. Geometrically speaking, though, conic sections, and the reason they get their name conic section is because the curves that you get when you look at these types of equations are intersections of a plane and a pair of hollow cones. And here's a link to a video. I'll also provide the link when I post this introduction so that you can watch that video. But it shows you how all of the conic sections are really an intersection of a plane and a pair of hollow cones. And so that's why we call them conic sections. Even though algebraically speaking, it's like, what does this have to do with a cone, right? But you get the idea when you look at the geometry of it. Okay. Now, the intersections of these three-dimensional objects are really two-dimensional cross-sections, so they can be described as a set of points in a plane. And that's what we're going to do. When we go through the conic sections in 5.1 and 5.2, we're going to go through each type of conic section, circles, parabola, hyperbola, and ellipses. We're going to look at each one, and we're going to look at their planar description. So we're going to look at them in terms of how we describe them as points in a plane. In order to understand that description, we need to understand the distance formula really well. I'm sure that you've seen the distance formula before, but just in case you haven't, here it is in all its glory. And I'm going to prove the distance formula to you. Right? So let's say that x1, y1 and x2, y2 are 2 points in a plane. The distance between them is the square root of x2 minus x1 squared plus y2 minus y1 squared. And here's how we know that. So let's say that we have a couple points, x1, y1, and x2, y2. The distance between these points is just this straight line here, right? This is the distance d. Okay? Now, if you make a right triangle out of this, then you know that the distance from here to here is going to be x2 minus x1. So this is x2 minus x1. And the distance from here to here is going to be y2 minus y1. So that distance right there is y2 minus y1. Okay, so now if you use Pythagorean Theorem, you know that x2 minus x1 squared, right, leg squared plus leg squared, right, y2 minus y1 squared equals d squared. Now take the square root of both sides and you end up here, right, d equals the square root of this stuff. So there's the distance formula for you. If you know Pythagorean Theorem, then you don't need to memorize the distance formula. You can just derive it on the spot. Okay. So we're going to spend several sections talking about conic sections in this chapter, but we're also going to spend a few sections talking about polar equations. Polar equations are just another way to represent relations instead of describing them in terms of their distance from the origin, their vertical and horizontal distance from the origin. We can describe them as their distance from the origin and the angle that they make with the positive x-axis. We kind of did this already when we were looking at complex numbers and de Moivre's theorem. Okay, but we're going to talk about polar equations in more detail during the second half of this chapter. So this chapter really has two main points, conic sections and then polar equations. When we're dealing with polar equations, we're going to use polar graph paper. So on the second page of this introduction, I have a bunch of polar graph paper for you, which you can print off and use when you're doing your homework if you'd like. You can also just Google polar graph paper and find a different set of graph paper if you like something better than what I have here. I'm not going to be offended, okay? But I did want to include this for you in case you wanted to print off a bunch of these to use in your homework. That's all I have to say by way of introduction to this chapter, so we'll see you in 5.1.